So I think it is time to move on to the next topic, resonance structure. Let me start writing a Lewis dot structure. We all can do this together. For a simple molecule, we did couple of molecules. We can take one of these as well, but we will do that later. Let's take a simple molecule like nitrate ion. I'm not sure whether we have done it before. If it is done, it's okay. So nitrate ion. So if I write the Lewis dot structure, I'll do it quickly because we know the process, we know the drill now. The number of valence electrons, nitrogen is 5, oxygen 6, times 3 because there are 3 oxygens, and this is an anion, negative ion. There is only one, so you have to add 1 electron. So that is your total valence count, which is 24. Nitrogen is the central atom. There are 3 oxygens as terminal atoms. And let's create the skeletal structure. So out of 24, we used 6. There are 18 left. Now you go to terminal atoms and complete their octet. 6 here. That oxygen is happy. 6 there. That oxygen is happy as well. And then 6 on the last oxygen. So 6 times 3, 18. So there were 18. We used all 18. Now we don't have any valence electrons. The central nitrogen does not have 8 electrons. Oxygens are happy. Oxygens have 8 electrons. Now let's make it 8. So I can take one of these pairs and share with nitrogen. If I do, what I get is this. So I'm going to make a double bond between nitrogen and oxygen. So now this oxygen will have 2 electron pairs. The others will have all 3. So this is nitrate ion. So that is the Lewis dot structure for nitrate ion. If we calculate the formal charges, nitrogen is +1. We cannot make it to 0 because it is nitrogen. So this is -1, this is -1, this is 0. So when I make that double bond, I use the electrons, the pair of electrons from this oxygen. So if you want, you can take a pair of electrons from other oxygen and create the double bond. Let's say I'm going to take, let's label this oxygen so that it's easier for me to say. Let's say this is oxygen A, this is B, and this is C. For the first structure, we created the double bond using a pair of electrons from oxygen A. Now I am going to do the same using oxygen B, not A. In that case, what I get is, I get a similar structure, but only the position of that double bond is going to be different. So now we are making the double bond here between this oxygen and nitrogen. So this will have 2 pairs, the others will have 3. So nothing complicated there, right? We basically took a pair of electrons from another oxygen. Now if you look at the first structure, this one, and the second one, it is nitrate ion. But the difference is, now the location of that double bond is different. We created the double bond using a different oxygen. If you want, you can use oxygen C. Let's do it quickly. Take the pair of electron from oxygen C and create the double bond. If I do that, what I get is this. So now I create the double bond between this oxygen and nitrogen. This will have 6 electrons. This will have 4. This will have 6, and it is nitrate ion. So if you look at closely these 3 structures, they look similar. Only difference is the location of that double bond. So we call these resonance structures of nitrate ions. So we just represent it in this way, double-sided arrow. So that double bond, it's like walking, right? It's like walking throughout the molecule. In a given time, we cannot say for sure the double bond is between oxygen A and nitrogen. We cannot say that. We cannot say the double bond is between nitrogen and oxygen B. It is not fixed. So I want you to understand that. We have not formally defined what resonance is yet. Okay, I'll do it in a second, but I want you to see the difference in these structures. Okay, let's look at what a resonance structure is. So it is a Lewis dot structure. It has the same skeletal structure similar to other structures of the molecule, but the difference is the electron arrangement. Electron arrangement is different. So it is formally written here. I want you to read it and understand. So this is a Lewis dot structure with same skeletal structure but different electron arrangement. So we can see that, we could see that in here. So this has the same skeleton but electron arrangement is different. What I mean by that is, in one structure, for example, structure 1, that oxygen A and nitrogen has a double bond, so oxygen A has 2 lone pairs. But if you go to structure 2, oxygen A has 3 lone pairs, a single bond. Now the oxygen B has 2 lone pairs and a double bond. So electron arrangement is different. So these are called resonance structures. Nitrate ion has 3 resonance structures. So I want you to understand this. In reality, if we experimentally measure strength of all 3 nitrogen oxygen bonds are the same and the bond length are the same as well. But if you look at the structure, one is a double bond and the other 2 are single bond. It looks like they are different. But in reality, when we experimentally measure this, they have the same bond length. So what it means is, in reality, nitrate ion looks like this. All 3 bonds are the same. If you think about bond length, it is between a double bond and single bond. So it is like an intermediate. It is longer than a double bond. It is shorter than a single bond. So it is in between. So if I write it in this way, so I assume you understand this point. So if you measure it experimentally, you don't see a bond length for a double bond, you don't see a bond length for single bond, but we see something in between. Let's have a look at this molecule. We did the Lewis dot structure of this molecule before, but in this molecule I just copied from there, but I have not made the double bond yet. So in our previous work, we made the double bond between nitrogen and oxygen D. In addition to that, I can make the double bond between nitrogen B and oxygen C. Doable, right? There is no problem there. So let's make those 2. So the first one I'm going to make between nitrogen B and oxygen D, so that this oxygen will have 2 pairs left and nothing happens to this oxygen. This has 2. Next one is, I can make the similar double bond using nitrogen B and oxygen C. So now this oxygen has 6 electrons, 3 pairs. We create a double bond between nitrogen B and oxygen C. Then oxygen C will have 4 electrons. Nothing happens to this pair. Now you can see that we just moved the double bond. We created the double bond somewhere else. So you can see that these 2 are resonance structures. The skeletal structure is the same, only the electron distribution is different. So now we have created 2 resonance structures. Can we make any more? I guess we can make another one. So what if I take that lone pair on nitrogen A and share it with nitrogen B? So in that case I can create this structure. So nothing happens to these 6 oxygens. Nothing happens to these 6 on oxygen D. Now we gave that the pair of electron on nitrogen A and share it with nitrogen B. That creates a bond between 2 nitrogens. Now again, if you check, all do have their octets except hydrogen. Hydrogen has duet. So now we have 3 structures. So this is the 3rd resonance structure of that molecule. So we can create 3 resonance structures for this skeletal structure I have given you. If I ask you this way, which one is the most stable one? To answer that question, we have to look at formal charges. Let's quickly figure out formal charges of each and every element in 3 structures. Let's start with the first one. So this oxygen is 0, this oxygen is -1, the nitrogen B is +1, nitrogen A is 0, hydrogen is 0. Let's go to the second structure. In that case, oxygen D is -1, oxygen C is 0, nitrogen B is +1, nitrogen A is 0, hydrogen is 0. Again, if you don't know how to calculate this, please check the previous video. Let's do the same for the third structure. Oxygen D is -1, oxygen C is -1, nitrogen B is +1, nitrogen A is again +1, hydrogens are zeros. So those are the formal charge distribution. Now we have to decide by looking at formal charge distribution which one is stable. If you look at the last structure, this one, there are 2 positive formal charges close to each other. There are 2 formal charges close to each other on 2 nitrogen. That is unstable, because 2 same type of charges, they don't like to be close to each other because they don't like each other. So because of that reason, the third structure is unstable. So this is unstable. Let me write why. I just said it, but let me write it in words. But if you look at the structure 1, this one. So oxygen has the negative formal charge, which is good, because most electronegative elements must have negative formal charges. So nitrogen has +1. Those are opposite charges, plus and minus. So this one is a stable structure. So why? Because the opposite charges are close to each other. If you look at the second structure, it is similar, right? So nitrogen has +1, oxygen has -1, so the opposite charges are close to each other. So this is stable as. So if I write this in words, you will realize this when you read notes. So the structure 1 and 2, they are stable. Structure 3 is unstable. But still there are 3 resonance structures. I assume you understand. If you don't, please watch the first video and go through the process and see how to calculate formal charges and how to write Lewis dot structure. Then it should be easier. So let's look at the next topic, bond polarity.